Right now, you believe you are made of atoms, solid little spheres clicking together to form your hand, your heartbeat, the screen glowing in front of you. That belief is comforting. It is also wrong. Beneath the atom lies a particle. Beneath that particle lies a smaller one. And beneath that, something so strange physicists stopped calling it matter. Tonight we descend through every layer of reality until we reach the place where existence begins to flicker. Before we go, leave a soft like so this journey finds another curious mind, and subscribe to fall asleep learning something vast. And tell me, where are you listening from tonight, and what hour rests around you? Take a slow breath, settle in. Before we begin the descent, let us stand for a moment on familiar ground. You already know what matter is. You learned it in a classroom with fluorescent lights and a poster on the wall. You learned that everything you can touch is made of atoms. The chair beneath you, the pillow under your head, the skin of your own hand, all of it built from tiny particles too small to see, arranged in patterns too intricate to imagine. You were shown a picture. A round nucleus at the center, and tiny electrons circling it like planets around a sun. A miniature solar system, neat and orderly, repeating itself 1 trillion times over inside every grain of sand and every drop of rain. That picture made sense. It still makes sense. And tonight, before we take it apart, we are going to honor it. Because the picture is not wrong, not exactly. It is simply incomplete. The story of how humans arrived at the atom is one of the most patient stories our species has ever told. It begins more than 2,000 years ago, in the warm coastal air of ancient Greece, where a philosopher named Democritus sat with a question that had no answer. Suppose you take a stone, he asked, and you break it in half. Then you break one of the halves in half again, and again, and again. Could you keep going forever, splitting each piece into smaller pieces without end? Or would you eventually arrive at something so small that it could not be split at all? Democritus believed in the second possibility. He believed that at the bottom of every material thing there must be a smallest piece, a final unit that nothing in the universe could divide any further. He called this piece atomos, a Greek word meaning uncuttable, the uncuttable thing, the end of the line. He could not see it, he could not test for it. He simply reasoned that it had to exist, because the alternative, an infinite descent into smaller and smaller fragments, felt wrong to him in a way he could not fully explain. He was right. He was also, as you will soon learn, profoundly wrong about what he was right about. For 2,000 years, his idea drifted through human thought, like a seed waiting for soil. Aristotle dismissed it. The medieval philosophers ignored it. The alchemists chased after gold and missed it entirely. The atom sat patiently in the margins of human imagination, waiting for someone to take it seriously again. And then, in the early 1800s, an English chemist named John Dalton picked up the seed and planted it. Dalton was a careful man, a Quaker schoolteacher who studied the weather and kept meticulous records of every measurement he ever made. He was not looking to reinvent the universe. He was looking to understand why certain chemicals combined in certain proportions and not others. Why 8 grams of oxygen would always bond with 1 gram of hydrogen to make water, and never 7 grams, and never 9. The numbers were too consistent to be a coincidence. There had to be a reason. So Dalton proposed something radical. He suggested that every chemical element was composed of tiny, indivisible particles, each one identical to every other particle of the same element. Hydrogen atoms were all the same. Oxygen atoms were all the same. And when they combined, they did so in whole number ratios, 2 of these to 1 of those, because you could not split an atom in half any more than you could split a person in half and expect them to keep walking. He sketched the first diagrams, little circles with letters inside them. The atom had entered the modern world. For the next 100 years, scientists worked under Dalton's assumption that the atom was a tiny solid ball, the smallest piece of matter, the bottom of the staircase. They built entire fields of chemistry on this foundation. They predicted reactions. They synthesized new compounds. They mapped the periodic table. The atom was useful, and the atom was simple, and nobody had any particular reason to look inside it. Because by definition, there was nothing inside it. It was the end of the line. And then a New Zealand-born physicist named Ernest Rutherford did something that shattered the comfortable picture forever. He fired bullets at it. Let me describe the experiment to you, because the image is worth holding in your mind. Imagine a thin sheet of gold foil, beaten so impossibly fine that light passes through it, so thin that it is only a few hundred atoms thick. Now imagine a small lead box on one side of the foil, with a tiny opening that aims a stream of alpha particles directly at the gold. Alpha particles are small, dense, positively charged fragments emitted by certain radioactive elements. They travel fast, and they carry energy, and at the time of Rutherford's experiment in 1909, they were the closest thing humans had to a microscopic bullet. Rutherford and his students set up a screen all around the gold foil, coated with a substance that glowed faintly when an alpha particle struck it. The plan was simple: fire the particles, watch where they land, use the pattern to figure out what the gold atoms looked like inside. The expected result was straightforward. According to the picture of the atom that everyone accepted at the time, an atom was a kind of soft cloud of positive charge, with electrons embedded inside it like raisins in a pudding. The alpha particles should pass through the gold foil almost undisturbed, deflected only slightly by the diffuse cloud. That is what everyone expected to see. That is not what they saw. Most of the particles did pass straight through, just as predicted, but a few, a very small few, did something impossible. They bounced back. Some of them came almost straight back toward the source, as if they had struck something solid and unimaginably dense in the otherwise empty foil. Rutherford himself later said it was as if you had fired a 15-inch artillery shell at a piece of tissue paper, and the shell had ricocheted off the paper and come back to hit you. There was something hard in there, something tiny, something concentrated, something with so much mass packed into so little space that it could turn a speeding bullet around and send it home. Rutherford had not just found the atom, he had found the inside of the atom. He had found the nucleus. And here is where your school picture begins to take shape. The nucleus at the center, dense and heavy and positively charged. The electrons whirling around it at unimaginable speeds, kept in their orbits by electromagnetic attraction. A miniature solar system, a tiny machine of perfect geometry. The image you grew up with. The image painted on the side of nuclear reactors and printed on the covers of science textbooks all over the world. It is a beautiful image. It is also mostly empty space. This is the part that nobody warns you about in school. Or if they mention it quickly and move on, because the implication is too strange to sit with for long. The atom is not a tiny solid ball. It is not even mostly solid. The atom is, by a margin so enormous, it defies intuition, almost entirely nothing. Let me give you a way to feel this. Imagine you could take a single atom and expand it to the size of a cathedral. A tall European cathedral with vaulted ceilings and stone walls and stained glass windows. Now, stand inside that cathedral and look for the nucleus, the thing that contains nearly all of the atom's mass, the dense, heavy, central core that defines the entire identity of the atom. Where is it? It is a single grain of sand, suspended in the air, somewhere near the center of the nave. That is the ratio. That is the geometry of solid matter. A grain of sand inside a cathedral. The rest is air. The rest is silence. The rest is the empty space through which a few electrons flicker, smaller than the grain of sand by a factor too large to name comfortably. your hand resting on the blanket right now, your chest rising and falling with each breath, the mattress holding the weight of your body. All of it is built from these cathedrals of emptiness, stacked side by side, trillions upon trillions of them, in such impossibly tight arrangement that they appear to your senses as something solid. You have spent your entire life touching things that are not really there. You have spent your entire life resting your weight on a structure that is mostly absence. Sit with that for a moment. Let it become beautiful instead of unsettling, because this is not a trick. This is not a hidden flaw in the universe. This is simply the truth of what you are made of. You are not a body of stone. You are a vast and intricate lattice of almost nothing, held together by forces too subtle for your senses to detect, persisting moment after moment in a configuration we call you. And yet, even this picture, the cathedral and the grain of sand and the small electrons whirling at the edges, even this picture is still wrong, still incomplete, still hiding something deeper. Here is the first quiet crack. The electron, the thing we draw as a small ball orbiting the nucleus, the thing your textbook shows as a tiny sphere on the end of a curved line, has never actually been seen as a ball. Nobody has ever photographed a spherical electron. Nobody has ever held one still long enough to measure its diameter. Nobody has ever observed an electron tracing a smooth elliptical path around a nucleus, the way the moon traces a path around the Earth. The picture in your textbook is a useful fiction. A diagram drawn for children and adults who needed something to hold in their mind while they learned about chemistry. The real electron does not behave that way at all. When physicists actually probe the electron, they find something far stranger. They find a smear, a cloud of probability, a presence that exists in many places at once and chooses a definite location only in the moment of being measured. The electron does not orbit the nucleus the way a planet orbits a sun. The electron exists in a kind of standing wave around the nucleus, a three-dimensional pattern of possibility that has no defined position until something forces it to declare one. When you sketch an electron as a tiny ball in a textbook, you are sketching a ghost, a convenience, a polite lie that helps the diagram make sense. I will not unpack this yet. We are not there. We are still standing in the doorway of the descent, and I want you to feel the first whisper of vertigo before we step through. The thing that holds your atoms together, the thing that gives shape to every solid object you have ever touched, is not a particle in any sense you would recognize. It is something else, something that does not quite belong to the category of thing at all. Hold that discomfort gently. It will grow. For now, let us return to the picture. Let us return to the friendly diagram. The nucleus at the center, the electrons whirling at the edges, the cathedral of empty space between them. Let us accept this picture as our starting map and prepare to walk further inward. Because if the atom is mostly empty and the electrons are not quite what we thought they were, then the entire weight of solid matter, the entire heaviness of your body and your bed and the earth itself, rests on the shoulders of one thing, the nucleus, the dense grain at the center of every cathedral, the small, heavy heart of every atom in existence. And we have been treating the nucleus, until now, as if it were itself a single solid object, a tiny ball of mass and charge, sitting quietly at the center of the atom, indivisible and complete. The end of the line, the bottom of the staircase, the last word. But the nucleus is not the bottom. The nucleus is a beginning. Inside the nucleus there are protons. Inside the nucleus there are neutrons. And inside the protons and the neutrons, packed into a space so small it makes the atom itself look enormous by comparison, there is something else, something stranger. Something that does not want to be seen alone, and that has never, in the entire history of human inquiry, been pulled out and shown to us in isolation. We are about to go there. We are about to step past the diagram you learned in school, past the cathedral and the grain of sand, past the smear of the electron cloud, and into a place where the words solid and empty and even particle begin to lose their meaning. Take one more slow breath. The descent begins now. In the late 1960s, in a long, low building stretching across the dry hills south of San Francisco, a group of physicists prepared to do something nobody had ever done before. They were going to look inside a proton. The building was called the Stanford Linear Accelerator. From above, it looked like a strange concrete spine laid across the California landscape, more than 2 miles long, perfectly straight, pointing toward nothing in particular. Inside that spine, electrons were accelerated to speeds so close to the speed of light that the difference becomes a mathematical curiosity rather than a physical one. The electrons were then aimed at a small target containing hydrogen, the simplest atom in existence, whose nucleus is nothing more than a single proton. The experiment was inspired by Rutherford. The same approach. Fire small, fast particles at something and see how they bounce. If the proton was a smooth, featureless ball of charge, the electrons would pass through it with only gentle deflections, scattering in a soft cloud around the target. That was what most physicists expected to see. The proton was already considered fundamental. It was already the supposed end of the line. It was supposed to be, like the atom before it had been, the bottom. The electrons did not behave the way a smooth ball would have asked them to behave. Some of them bounced back at sharp angles. Some of them ricocheted as if they had collided with something hard and small inside the proton. Something with definite edges. Something with structure. The proton was not smooth. The proton was not a single thing. The proton was a container. The physicists running the experiment called the mysterious objects inside partons, a placeholder name that meant nothing more than parts. They knew something was in there. They did not yet know what. The data showed 3 small dense centers inside each proton, 3 points of focused interaction, 3 little knots of something around which the rest of the proton seemed to organize itself. 3. Always 3. In the same years, working from a different direction entirely, a theoretical physicist named Murray Gell-Mann had been playing with a strange mathematical pattern. He had noticed that all the particles physicists had been discovering, the strange particles streaming out of cosmic ray collisions, the hadrons spilling from early particle accelerators, the bewildering zoo of new things that had appeared in the laboratories of the 1950s, all of them seemed to fit into neat geometric arrangements when sorted by their properties. Triangles, hexagons, patterns that suggested something deeper underneath, the way a row of repeating shapes in a tile floor suggests a hidden grid beneath the surface. Gell-Mann proposed that the pattern existed because the particles were not fundamental. They were built from smaller pieces. 3 pieces, for most of them, pieces nobody had ever seen. He gave them a name, plucked in a moment of literary playfulness, from a line in a novel by James Joyce. He called them quarks. When the Stanford experiments revealed 3 small centers inside the proton, the world had its answer. The quarks were real. The proton was not the bottom. The bottom had moved again. I want you to sit with the strangeness of this moment in human history. For thousands of years, the atom had been the smallest thing. Then, in the early 1900s, the nucleus had been the smallest thing. Then, for half a century, the proton and the neutron had been the smallest things. And now, in the span of a single decade, the proton and neutron had themselves cracked open and revealed something smaller, something that nobody had predicted, nobody had photographed, and nobody, as it would soon turn out, would ever be able to hold in isolation. The quarks came in flavors. That is the technical word physicists chose, and you should hear it the way they intended it, not as a description of taste, but as a kind of label, a way of marking one variety from another. There are 6 flavors of quark. I am going to name them slowly, because the names themselves carry the strange poetry of mid-20th century physics, and because hearing them in sequence gives you the feeling of being handed a hidden alphabet that the universe has been using all along to spell itself. The up quark, the down quark, the charm quark, the strange quark, the top quark, the bottom quark. 6 flavors, 6 fundamental ingredients. From these 6 small things, every proton and every neutron and every more exotic particle ever observed in a collider can be built. But for the matter that makes up you, and the matter that makes up your home, and the matter that makes up this planet, and every star you can see in the night sky, only 2 of the 6 are needed. The up and the down, that is it. 2 flavors of quark, arranged in groups of 3, glued together inside protons and neutrons. And from that arrangement comes all the heaviness, all the substance, all the apparent solidity of every object you have ever touched. A proton is 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up quark. That is the entire recipe for the matter of the visible universe. 3 quarks in 2 different combinations, repeated endlessly in the heart of every atomic nucleus. From this tiny pattern, all the diversity of the material world is constructed. The water in your glass, the iron in your blood, the carbon in the page of every book ever written, all of it, at the bottom, is just up quarks and down quarks arranged in 3s. And here is where the wonder begins to deepen, because the quarks are not behaving the way anything else in your experience behaves. The quarks have never been observed alone. I want you to feel the weight of that sentence, not a casual statement, not a technological limitation that future experiments might overcome, a fundamental rule of nature. In every collider, in every particle accelerator, in every cosmic ray collision ever recorded, a quark has never been pulled out of a proton or a neutron and shown to us in isolation. Not once, not ever. They cannot be separated. They cannot be displayed individually. They live their entire existence in groups, locked inside the particles they help to compose, refusing to be alone. The reason is one of the strangest discoveries in the history of physics, and it has a name that sounds almost gentle until you understand what it means. It is called confinement. The force that binds quarks together is called the strong nuclear force. It is the most powerful of the 4 fundamental forces of nature, stronger than gravity by a factor that has more zeros than your patience can hold, stronger even than the electromagnetic force that keeps the atoms in your body from flying apart. The strong force is what holds the nucleus together. The strong force is what allows protons, which are all positively charged and would otherwise repel each other furiously, to nestle quietly side by side in the heart of every atom. The strong force is what makes matter possible at all, and the strong force behaves in a way that nothing else in your everyday experience behaves. Think for a moment about gravity. The further you move 2 objects apart, the weaker the gravitational pull between them becomes. Walk away from the Earth and you feel lighter. Travel far enough into space and the Earth releases its hold on you entirely. The same is true of magnetism. The same is true of static electricity. The same is true of every familiar force you have ever encountered. Distance weakens the pull. Distance is what allows separation to happen. The strong force does the opposite. The further you try to pull 2 quarks apart, the stronger the force between them grows. Imagine a rubber band stretched between your hands. As you pull your hands further apart, the band stretches and the tension in it increases. Now imagine a rubber band that grows infinitely strong as it stretches. Imagine a rubber band that no matter how much energy you pour into it, never lets go, never relaxes, never reaches a point where you can finally separate your hands. The harder you pull, the more the force pulls back. The further the quarks travel from each other, the more violently they are dragged together again. And here is where it becomes truly strange. If you do somehow manage to pour enough energy into the gap between two quarks to try to separate them, the energy itself spontaneously transforms. It becomes new quarks. The space between the two quarks fills with newly created matter, fresh quarks appearing from the input of energy, instantly pairing with the quarks you were trying to separate, so that what you end up with is not two free quarks, but four bound quarks in two new configurations. The universe will not allow a quark to stand alone. It will spend energy. It will create matter from nothing rather than permit the isolation of a single quark. Pause and feel that for a moment. Nature itself refuses to let us see these things by themselves. The deepest building blocks of all matter in the universe are forbidden by the laws of physics from ever appearing in solitude. They exist only in groups. They exist only in relationship. The fundamental ingredients of reality are not independent objects. They are inherently social. They are inherently bound. The particle that mediates this strange, growing, unbreakable force has a name as plain as a hardware store. It is called the gluon, the thing that glues. There are 8 different varieties of gluon, and unlike most other force-carrying particles, the gluons themselves carry the same charge they are responsible for transmitting. This means the gluons can interact with each other. They can bind to other gluons. They can form their own little structures inside the proton, swarming and weaving and exchanging energy in a constant restless dance that nobody can directly see, but everyone can measure. The inside of a proton, when you look at it carefully, is not a quiet little arrangement of 3 small balls held together by a few obedient threads. The inside of a proton is chaos. The inside of a proton is a boiling sea. The 3 quarks are there, yes, but they are surrounded by a churning storm of gluons, and within that storm, virtual quarks and antiquarks are constantly flickering in and out of existence, born from the energy of the gluons and absorbed back again before they can be properly counted. The proton is alive in a way that defies the simple diagrams. The proton is a tempest in miniature. And now I have to tell you something that I want you to sit with carefully, because it changes the meaning of substance itself. The quarks, the 3 small, heavy things at the supposed center of the proton, do not actually contribute most of the proton's mass. The mass of an up quark and the mass of a down quark are tiny, almost negligible. If you took the 3 quarks inside a proton and added their individual masses together, you would get less than 1% of the total mass of the proton. Less than 1%. The other 99%, the overwhelming majority of what we call the mass of ordinary matter, does not come from the quarks at all. It comes from the gluons. Or, more precisely, it comes from the energy of the gluon field. The constant churning of the strong force, the unending storm of bound interaction inside the proton, the tension, the motion, the ceaseless work of holding the quarks together. That energy, by Einstein's old and patient equation, possesses mass. Energy and mass are the same currency, exchanged at the rate of the speed of light squared. And the energy stored in the bonds inside every proton is so enormous that it accounts for almost all of the weight of every atom in your body. Let that settle. Your body feels heavy because of the chair it presses against. The chair feels heavy because of the floor it stands on. The floor feels heavy because of the planet that holds it. And all of that weight, every gram of it, every pound of it, can be traced backward through the layers of matter to the protons and neutrons in the atomic nuclei that compose every cell of every object involved. And nearly all of that weight is not stuff. It is not substance. It is not the heaviness of small solid things piled together. It is the energy of bonds. It is the tension of invisible forces holding invisible particles in invisible relationship. Mass is not stuff. Mass is tension. Mass is the energy of binding, the work of confinement, the ceaseless internal motion of fields and forces that refuse to be still. Your body, which feels so solid and so present and so undeniably real, is mostly the music of bound energy. You are not heavy because you contain heavy things. You are heavy because something inside you is working ceaselessly to hold itself together. Sit with that. Breathe with it. Let it become something other than terrifying. Because the obvious question now rises, and your mind has probably already begun to ask it. If the proton is made of quarks, and the quarks are held together by gluons, then what are the quarks themselves made of? Are they balls of something smaller? Are they vibrations of something deeper? Are they truly the bottom of the staircase? Or have we simply reached another false floor, with another set of doors waiting to be opened beneath it? The honest answer, the answer that modern physics gives, is that we do not know. For the moment, in every experiment we have ever conducted, the quark behaves as if it has no internal structure. It behaves as if it is genuinely fundamental, a point without dimensions, a thing without parts. We can push it to the highest energies our machines can reach, and the quark gives no sign of breaking open the way the proton did. No internal centers, no hidden grains, no partons within the parton. As far as we can currently tell, the quark is one of the smallest meaningful units of matter in the entire universe. But you should hear that statement with some healthy skepticism. The proton, too, was once thought to be fundamental. The atom, too, was once thought to be the bottom. Every generation of physicists has stood on what they believed was the deepest floor of reality, and every generation has eventually discovered another room below. There is no reason yet to believe that the quark is special. There is no theorem proving that the descent must stop here, and there is something else. Something that should make you uneasy in the most productive way possible. Because even if the quark really is fundamental, even if it really is a point particle with no internal structure, there is still a question we have not yet asked. We have been speaking about quarks as if they were small things, tiny balls of matter, hidden inside the proton, held together by gluons. We have been picturing them the way Democritus would have pictured them, as objects, as stuff. But what if the quark is not an object at all? What if none of these particles, not the electron, not the quark, not the gluon, none of them are really objects in the way we have been imagining? What if the entire vocabulary of small things and tiny balls and miniature parts is itself the next picture that needs to be dissolved? We are about to take another step inward. We are about to leave behind the comfortable image of the particle as a little piece of matter and enter a world where the very word particle begins to mean something entirely different. A world where reality is not built out of objects at all, but out of something far stranger, something that fills all of space at once, something that does not sit, but vibrates. Hold the descent. Stay with me. Before we go any deeper, before we let go of the comfortable word particle entirely, I want to widen the lens. I want to show you the full inventory. I want to walk you through the most successful theory humans have ever written, the closest thing our species has produced to a complete catalogue of reality. It is called the Standard Model of Particle Physics. The name is plain, almost humble, in the way that physicists often choose names. There is no poetry in it, no grandeur. It does not announce itself as the theory of everything or the equation of God. It simply calls itself a model, a working framework, the standard one. And yet, behind that modest title sits an achievement so staggering that it is difficult to describe without sounding as though you are exaggerating. The Standard Model is the most precisely tested theory in the entire history of science. Its predictions match experimental measurements to a degree of accuracy that has no equal anywhere else in human knowledge. Some of its calculations agree with reality to more than 10 decimal places. 10 decimal places. That is the equivalent of measuring the distance from your front door to the moon and being wrong by less than the width of a single human hair. This is the theory that says what reality is made of. So let us look inside it. The Standard Model divides everything into two great families: the matter particles, the things that compose substance, and the force particles, the things that transmit interaction between matter. The matter particles are called fermions. The force particles are called bosons. You do not need to remember the names. You need only to feel the shape of the architecture. Stuff on one side, the forces between stuff on the other. Two columns, two halves of the universe. The matter family contains 12 members, 12 fundamental particles, from which all the substance you have ever encountered is built. 6 of them are quarks, and you have already met them. The up, the down, the charm, the strange, the top, the bottom. The other 6 belong to a family called the leptons, and most of them are strangers to you, even though one of them has been your constant companion since the moment you first opened your eyes. The leptons begin with the electron, yes, the same electron that orbits the nucleus in your school textbook, the same electron that whirls around every atom in your body right now. The electron is a lepton. It does not feel the strong nuclear force. It does not live inside a proton. It belongs to a different category of fundamental thing, lighter, freer, more solitary, content to drift in clouds around atomic nuclei rather than locked away inside them. The electron is the most familiar member of the lepton family, the one you have known your whole life without knowing its surname. The other 5 leptons are stranger. There is the muon, which is essentially a heavier cousin of the electron, the tau, which is heavier still, and then there are the 3 neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. The neutrinos are perhaps the strangest matter particles in the entire Standard Model. They have almost no mass. They interact with ordinary matter so weakly that trillions of them are passing through your body right now, streaming out of the sun and the stars and the cosmic background, and you cannot feel them. You will never feel them. They pass through you the way light passes through glass, almost as if you were not there at all. So that is the matter half of reality. 12 particles, 6 quarks, 6 leptons. From these 12 ingredients, in different combinations, every atom in every star, in every galaxy, in the observable universe is built. The chair beneath you, the hand resting on the blanket, the breath leaving your mouth. All of it, at the deepest level, is some arrangement of these 12 fundamental things. But matter alone does nothing. Matter sitting in space without interaction is meaningless. For anything to happen, the particles of matter must communicate with each other, must push and pull, and exchange and bind. That is the work of the force particles. The other side of the architecture, the bosons. There are 4 fundamental forces in the universe: gravity, which holds you to the earth, and the earth to the sun; electromagnetism, which governs every chemical reaction in your body and every photon entering your eyes; the strong nuclear force, which holds quarks inside protons and protons inside nuclei; and the weak nuclear force, which is responsible for certain types of radioactive decay and for the nuclear reactions that allow the sun to shine. Each of these forces, except for gravity, is carried by its own kind of boson. Electromagnetism is carried by the photon, the particle of light, every flash of color you have ever seen, every warmth you have ever felt from a fire or the sun, every electrical signal racing through every wire and every nerve in your body, is the action of photons being exchanged between charged particles. The photon is the messenger of light and electricity and magnetism, the most familiar boson, the one you have been seeing your entire life. The strong nuclear force is carried by the gluons. You have already met them, the 8 varieties of binding, the ceaseless storm inside every proton, the unbreakable rubber bands that hold the quarks in their forced companionship. The weak nuclear force is carried by two siblings called the W and Z bosons. The W comes in two charge varieties, positive and negative. The Z is neutral. Together, they govern the strange transformations that turn one kind of particle into another. They are why a neutron, left alone, will eventually decay into a proton, releasing an electron and a neutrino as it changes its identity. They are why the sun burns. They are why elements heavier than hydrogen exist at all. Gravity, alone among the forces, does not appear in the standard model. We will return to that absence later, because it is one of the deepest scandals in modern physics. For now, simply notice it. The standard model contains everything except the force that you feel most powerfully and most constantly, the force that holds you to your bed at this very moment. Gravity does not fit. The map of the smallest things has a hole in it shaped exactly like the largest thing. And then, at the very top of the diagram, sits one more particle, a particle that belongs neither to the matter family nor to the force family, a particle that is different from all the others, and that took the longest to find, and whose discovery in 2012 was perhaps the single greatest scientific moment of the 21st century so far. The Higgs boson. You may have heard it called the God particle, a nickname that physicists themselves dislike because it sounds dramatic in a way that the actual physics does not deserve. The Higgs boson is not a god. The Higgs boson is something far more interesting. The Higgs boson is the visible trace of a field, the Higgs field, which fills all of space at every point in the universe. And when other particles move through this field, the field grabs at them, slows them, gives them resistance. That resistance is what we call mass. The reason an electron has mass is that it interacts gently with the Higgs field. The reason a top quark is so much heavier than an up quark is that the top quark interacts with the Higgs field far more strongly. The Higgs field is the reason mass exists in the universe at all, the reason any particle has weight, the reason anything in your body is anything other than a beam of pure light. Without the Higgs field, every fundamental particle would travel at the speed of light, never slowing, never gathering, never binding into atoms or molecules or planets or people. Your existence depends entirely on the fact that this field fills all of space and softly drags on the particles that try to move through it. The Higgs boson is the proof that the field is real. It is the small detectable ripple, the local excitation, the rare and fleeting evidence that the field is there at all, and finding it took 50 years. Let me describe to you what humans built in order to see it. Beneath the border between France and Switzerland, in a circular tunnel that loops for 17 miles through the rock, there lies a machine, the Large Hadron Collider. It is the largest scientific instrument ever constructed by human beings. Its tunnel is buried more than 100 meters underground, deep enough that the surrounding countryside knows nothing of its existence. Inside the tunnel, two beams of protons travel in opposite directions around the ring, accelerated to within a hair's breadth of the speed of light. Each beam contains trillions of protons, packed into tiny bunches, racing through a vacuum more empty than the space between the stars. To keep these protons moving in their perfect circle, the tunnel is lined with thousands of superconducting magnets. Magnets so powerful that they require temperatures colder than the depths of empty space itself to operate, colder than the cosmic background radiation, colder than almost anywhere else in the known universe. To achieve this, the magnets are bathed in liquid helium at less than 2 degrees above absolute zero. Humanity, in order to glimpse a single fleeting particle, built a structure colder than the void between galaxies and ran beams of matter through it at nearly the speed of light. The two beams collide at specific points inside enormous detectors, machines the size of cathedrals, built to record what happens in the wreckage of each impact. When two protons strike each other at these energies, they shatter, and the energy of the collision spills outward as a shower of new particles. born from the kinetic energy of the impact, according to Einstein's equation. Most of these particles are familiar: quarks, electrons, photons. But occasionally, very occasionally, the conditions align such that the Higgs field itself is briefly disturbed, and a Higgs boson appears. It does not last. The Higgs boson is unstable. It exists for less than a sextillionth of a second. That is a 1 preceded by a decimal point and 20 zeros. A duration so short that light itself, the fastest thing in the universe, can travel only the width of an atomic nucleus before the Higgs boson is gone. We do not see the Higgs directly, we see its remains. The particles it decays into, the pattern of its disintegration. From the wreckage, we reconstruct the existence of the parent. On the 4th of July, in the year 2012, after 50 years of searching, after billions of dollars of investment, after the labor of thousands of scientists from dozens of countries, 2 separate teams at the Large Hadron Collider announced that they had found it. The Higgs boson was real. The Higgs field existed. The mechanism that gives mass to matter had been confirmed. I want you to feel the weight of this story, not just as a sequence of dates and machines, but as something else, as a kind of pilgrimage. Humanity, the smartest and most curious of all the species that have ever lived on this planet, spent half a century building the largest machine in history, cooled it colder than the void of space, accelerated matter to nearly the speed of light, smashed it together inside instruments the size of buildings, and did all of this in order to glimpse a single particle that exists for less than the time it takes light to cross an atom. We did this to see something that nobody could ever directly hold. We did this because we wanted to know. That is what science is when you strip away the equations and the budgets. It is a long, slow act of devotion. It is a pilgrimage of measurement. It is the patient willingness to build cathedrals of magnets in order to see the smallest things. And here, just as you are settling into the satisfaction of this story, just as you begin to feel that perhaps we have finally arrived at the bottom, I have to introduce the unease. Because the Standard Model, for all its precision, for all its triumph, for all its sextillionths of a second of perfect prediction, is incomplete. It does not include gravity. The force you feel right now, holding you to the planet, has no place in the catalogue. Every attempt to fit gravity into the Standard Model has produced equations that break, that produce infinite answers, that refuse to behave. There should be a graviton, a particle that carries the gravitational force the way the photon carries electromagnetism, but the graviton has never been observed, and the mathematics that should describe it does not work the way the rest of the model works. The largest force in everyday life is missing from the deepest theory of physics. It does not explain dark matter. When we look at galaxies, we see them spinning in ways that the matter we can detect cannot account for. There has to be something else, something invisible, something heavy and silent and pervasive, holding the galaxies in shape with its gravitational pull. Astronomers estimate that this dark matter makes up about 5 times as much mass in the universe as all the ordinary matter combined. 5 times more dark matter than every star and every planet and every cloud of gas in every galaxy you have ever heard of. And it is not in the Standard Model, not one particle of it. Whatever dark matter is, it is something the catalogue has failed to mention. It does not explain dark energy, which appears to be accelerating the expansion of the universe and which makes up an even larger fraction of the cosmos than dark matter does. It does not explain why the masses of the particles have the specific values they do. It does not explain why there are exactly 3 generations of matter rather than 2 or 4. It does not explain why our universe contains so much more matter than antimatter, when both should have been produced in equal amounts at the beginning of time. It does not explain how the universe began. The Standard Model is the most accurate theory ever written by humans, and it leaves out most of the universe. Here is the analogy I want you to hold. The Standard Model is like a library where every book is perfectly catalogued. You can walk in and you can look up any book you want, and the catalogue will tell you exactly where it sits. The shelves are clean, the numbering is precise, the cross-references all check out. It is a beautiful, working library, and within its walls, everything is in order. But the library itself sits on a foundation that nobody has ever inspected. There is a basement nobody has ever entered. There is a building plan nobody has ever read. There is a quiet suspicion among the librarians, growing year by year, that the books in the library represent only a small fraction of the books that exist, and that the rest are stored somewhere they cannot reach, in a structure they cannot see, by a librarian they have never met. This is the strange humility of modern physics. We have measured the smallest things with extraordinary care. We have built machines colder than the cosmos to glimpse particles that last less than a sextillionth of a second. We have predicted experimental outcomes with such precision that the agreement between theory and measurement is one of the great spiritual achievements of our species. And we still do not know what these things really are. Because, of course, hovering over the entire library, there is a question that has haunted physicists since the very beginning. A suspicion that has grown quietly in the background, decade after decade, as the catalogue has become more precise and the underlying foundation more mysterious. What if the particles in the Standard Model are not the bottom? What if they are not even particles? What if every name in the catalogue, every fundamental ingredient we have so carefully measured and named, is itself a kind of shadow, a surface effect? A useful description of something that is not really an object at all, but a pattern, a vibration, a ripple in something deeper that we have only just begun to notice. The Standard Model, for all its beauty, treats its particles as point objects, tiny dots without size, without internal structure, sitting at definite locations in space. But every measurement we have ever made of these things suggests that this picture, like the picture of the atom as a tiny solar system, is a useful fiction. The deeper you probe, the less the particle behaves like a particle. The deeper you probe, the more the entire vocabulary of small solid things begins to dissolve. What if there are no particles at all? What if there are only fields? We are about to step through the last door of the familiar. We are about to leave behind the comfortable image of reality as a collection of small objects and enter a world where the building blocks of existence are not things but disturbances, not stuff but patterns, not matter but music. Breathe slowly. The next descent begins. Here is where the language begins to break. For most of this descent, we have been using a word as if we understood it. Particle, a small thing, a piece of stuff, a miniature object with a location and a size and a shape. We have been picturing the electron as a tiny ball. We have been picturing the quark as a tinier ball. We have been imagining the entire universe as a kind of vast warehouse, stacked with smaller and smaller boxes, each one containing the next. That word, particle, is the next picture that has to dissolve. In the deepest and most accurate theory of physics that humans have ever written, there are no tiny balls. There are no miniature objects. There is no small solid stuff hiding at the bottom of matter, waiting to be photographed if only our microscopes grew strong enough. The bottom of matter is not made of things at all. The bottom of matter is made of fields. I want to introduce this word slowly, because everything that follows depends on you holding it carefully in your mind. A field, in physics, is not a thing. A field is a property that exists at every point in space. Think for a moment of temperature. The room you are in right now has a temperature, and that temperature is not the same in every corner. Near the window it may be cooler. Near the lamp it may be warmer. At every single point in the room, there is a specific value of temperature. The collection of all those values, spread across the entire room, is a temperature field. It is not a thing. It is not located anywhere in particular. It is a pattern of values that fills all of space. Now stretch that idea. Stretch it past the walls of your room. Stretch it past the roof of your house. Stretch it past the atmosphere of the Earth, and past the orbit of the Moon, and past the outermost planets of the solar system, and past the nearest stars, and past the spiral arms of the galaxy, and past every galaxy you can see and every galaxy you cannot see, all the way to the edge of the observable universe. Imagine a field that fills all of this. A field that has a specific value at every single point in the vastness of existence, from your eyelashes to the most distant quasar. This is what physicists mean when they say a field fills all of space. They do not mean some of space, they mean all of it. And here is the thing that changes everything. Every type of particle has its own field. There is an electron field, a real mathematical structure that exists at every point in the universe. Where the electron field is quiet and flat, you would say there are no electrons there. Where the electron field is disturbed, where it ripples, where a small localized vibration moves through it like a wave moving across a pond, you would say there is an electron at that location. The electron is not an object that moves through space. The electron is a disturbance in the electron field, a momentary peak in a pattern that fills the entire universe. There is a photon field, which we usually call the electromagnetic field. Every time light reaches your eyes, every time a star sends its glow across the void, every time a radio wave passes through your body, what is actually happening is that the electromagnetic field is vibrating. A photon is not a little particle of light traveling from a source to your eye. A photon is a ripple in the field that fills all of space, a localized excitation that carries energy from one place to another by disturbing the underlying pattern. There is a Higgs field. You have already heard about it. The field whose interaction with other fields gives those fields the property we call mass. The Higgs boson is not a tiny object that appears in colliders. The Higgs boson is a ripple in the Higgs field, briefly conjured by enough energy to disturb it, fading back into stillness almost as soon as it appears. There is an up quark field, there is a down quark field, there is a charm field, a strange field, a top field, a bottom field. There is a field for each of the 6 leptons, including the electron and the muon and the tau and the 3 flavors of neutrino. There is a gluon field. There are fields for the W and Z bosons. There are roughly 24 fundamental fields, depending on how you count, and each one of them fills all of space, and each one of them is currently humming and vibrating and rippling at every point in the universe, including the point in space where your body is located right now. Stop, slow down, sit with this. You are not a collection of small objects. You are not a pile of tiny balls stacked together into the shape of a person. There is no level at which you are made of stuff, in the way you have always imagined stuff. When you look at your hand resting on the blanket, what you are actually looking at is a complex, persistent pattern of vibrations in roughly 24 overlapping fields, all of which extend to the furthest reaches of the cosmos. The patterns in those fields, in the small region of space currently occupied by your body, happen to be arranged in such a stable and self-reinforcing way that we call them you. You are a standing wave, a configuration of ripples, a momentary knot in a vast and ancient music that has been playing since the beginning of time. The hand, the breath, the eyelid blinking once, slowly, over your eye. None of it is small things doing small motions. All of it is the local trembling of fields that reach across the entire observable universe. The same electron field that vibrates inside your fingertip is the same electron field that vibrates inside the heart of a star 14 billion light years away. You are connected to that star not by metaphor, but by mathematics. You share a field with everything. There is no electron field that belongs to you and a different electron field that belongs to it. There is one electron field, one, and you and the star are both ripples in the same surface. Breathe with this. Let it settle into your body. The implication is not that your life is unreal. The implication is that your life is real in a different way than you had assumed. You are not made of stuff. You are made of pattern. You are not a collection of objects. You are a configuration. You are a melody. The mathematical framework that describes all of this has a name. It is called quantum field theory. 2 words, 4 syllables, the most successful description of physical reality that humans have ever produced. The mathematics inside it is fearsome. Equations stacked on equations, integrals nested inside integrals, operators acting on operators in an alphabet of symbols that takes years of patient study to read fluently. Most physicists who use it every day will admit quietly that nobody fully understands what it means. The math works. The predictions come out correct to 10 decimal places. But the picture underneath the math, the question of what the universe actually is when described this way, remains a mystery that even the people who built the theory cannot fully unravel. The picture is poetic, even if the equations are not. Quantum field theory says that the universe is a vast collection of overlapping fields, each one filling all of space, each one capable of being disturbed, each one carrying its own kind of vibration when it is disturbed. Particles are not the basic ingredients of reality. Particles are temporary names we give to the disturbances. The deepest level of physics, as far as we currently understand it, is not matter at all. It is the ongoing trembling of fields. And here is where it becomes truly strange. Because the fields are quantum. You have heard the word quantum used as a kind of mystical adjective in popular culture, attached to everything from healing crystals to financial software, drained of its meaning. Let me give it back to you. In physics, quantum simply means that something comes in discrete packets rather than smooth amounts. Energy is quantum. It does not flow in any quantity you like. It arrives in specific minimum chunks. The ripples in a quantum field do not come in any size. They come in fixed minimum disturbances. Each minimum disturbance is what we call a particle. You cannot have half an electron. You cannot have a third of a photon. You can have 0, or 1, or 2, or 3, but never the smooth gradations that classical physics had imagined. This is why the world has the granularity that it has, why light comes in photons, why matter comes in atoms, why the universe, at the smallest scale, is not a smooth continuum, but a digital pattern of discrete excitations. The quantum nature of fields is the reason anything in the universe is countable at all. Without it, reality would be a smooth blur, and there would be no individual particles, no individual atoms, no individual you. Now hold all of this in your mind. The fields filling all of space, the vibrations rising as discrete particles, the intricate pattern of overlapping disturbances that we call your body. And ask one more question, because it leads to a place even stranger. What does it mean for a field to be empty? In classical physics, empty space is exactly what it sounds like. Nothing. A region where no matter exists. A volume of pure void. The space between the stars. The space inside an evacuated chamber. The space, if such a thing existed, between the smallest particles. Empty, quiet, featureless. In quantum field theory, empty space is not empty. Imagine a perfectly empty box. You have pumped out all the air. You have shielded it from all radiation. You have cooled it to as close to absolute zero as physically possible. By every classical standard, the inside of the box is nothing. There is no matter in it. There is no light in it. There is no energy in it. It is the most absolute emptiness you can engineer. In quantum field theory, the inside of the box is the most active place in the universe, because the fields are still there. The fields cannot be removed. The fields exist at every point in space, including every point inside your perfectly empty box. And the fields, even when they are not excited into the localized peaks we call particles, are still not perfectly still. They cannot be perfectly still. The mathematics forbids it. There is a fundamental restlessness in every quantum field, a kind of irreducible jitter, an unending tremor that physicists call zero-point fluctuation. The fields are always humming. The fields are always shifting. The fields are always doing something, even when the something is too small to register as a particle in any normal measurement. Inside your empty box, the fields are constantly generating tiny temporary disturbances. Pairs of particles and antiparticles flicker briefly into existence, born from the energy of the vacuum itself, and then annihilate each other and vanish before any instrument could possibly detect them. An electron and a positron, a quark and an antiquark, a pair of photons appearing back to back and immediately dissolving. The empty box is not empty. The empty box is a foam, a roiling sea of brief flickers, a surface of dark water on which countless small bubbles are constantly forming and bursting, too small and too fast to be seen with any direct instrument. The particles in this foam are called virtual particles. Virtual because they exist only briefly, on borrowed energy, returning that energy to the vacuum almost as soon as they appear. They do not last long enough to be considered real in the ordinary sense. But they are not imaginary. They are not a metaphor. Their existence has measurable consequences in the physical world. The most famous of those consequences is something called the Casimir effect. Imagine two flat metal plates, perfectly parallel, held extremely close together inside a vacuum. According to classical physics, there should be no force between them. The space between them is empty. The space outside them is empty. There is nothing to push them together and nothing to pull them apart. Classical physics predicts that the plates will simply sit there, motionless. In reality, the plates are pulled toward each other. The reason is the quantum foam. In the vacuum outside the plates, virtual particles of every wavelength can flicker in and out of existence, in a continuous spectrum of possible disturbances. But in the narrow space between the plates, only certain wavelengths fit. The plates restrict which virtual fluctuations are allowed to appear in the small region between them. As a result, there are fewer virtual particles between the plates than there are outside them. The pressure of the quantum foam on the outside is therefore greater than the pressure of the quantum foam on the inside, and the plates are pushed together by the difference. This force has been measured in careful experiments in real laboratories with real plates and real instruments. The predicted force has been detected and confirmed. The Casimir effect is real. The quantum foam is real. Empty space is not empty in the way that you have always assumed. Empty space is full of something. A ceaseless, restless background hum that has measurable physical consequences and that fills every cubic centimeter of every region of the universe, including the regions inside your own body. Sit with this for a long moment. Let it become almost too much. What you have always called nothing is in fact the loudest room in existence. The vacuum between the stars is not silent. The vacuum is roaring, not with sound, not with anything you could hear, but with the ceaseless creation and annihilation of fleeting particles, the ongoing trembling of every fundamental field, the unending music of zero-point energy. There is no place in the universe where this music stops. There is no region you could travel to that would be truly still. Even inside the deepest void between the most distant galaxies, the fields are humming. The foam is forming, the vacuum is alive, and you, your body, your breath, your beating heart, exist immersed in this vast restlessness. You are not surrounded by emptiness. You are bathed in an ocean of subtle activity that pervades every gap between every atom in your body. The space between your fingers is not nothing. The space inside your lungs is not nothing. The space within every cell of your bones and your skin is not nothing. It is foam, it is hum, it is the patient and unending tremor of fields that have been vibrating since the universe began. This is what reality looks like when you look at it through the lens of quantum field theory. Not a warehouse of small, solid things. Not a collection of tiny balls stacked into shapes. Not a universe of substance at all. A universe of pattern. A universe of vibration. A universe in which the very notion of empty is a kind of misunderstanding, and in which every cubic millimeter of every place in existence is a small symphony of ongoing disturbance, generating brief and shimmering ghosts that vanish before they can be named. And yet, even at this depth, even having dissolved the particle into the field and the field into the foam, the descent is not finished. Because the moment you have settled into this picture, the moment you have begun to feel that perhaps you have arrived at the bottom of reality, an even stranger question rises. What are the fields themselves vibrating in? A wave on the surface of a pond is a disturbance in water. A sound wave is a disturbance in air. A wave on a guitar string is a disturbance in the string. Every wave we have ever encountered in everyday life is a disturbance in some underlying medium, some substance that does the vibrating. The wave is not the thing. The thing is the water, the air, the string. The wave is just what the thing is doing. So what are the quantum fields vibrating in? What is the medium beneath them? What is the substance whose trembling we are calling the field? Is it space itself? Is it space-time? Is it something deeper still, some structure beneath the geometry of the universe, of which space and time are themselves only emergent patterns? And if the field is the disturbance in something even deeper, then perhaps the field is not the bottom either. Perhaps the entire descent, atom to nucleus to quark to particle to field, is only the first few steps in a staircase that continues much further down. Perhaps the true bottom of reality is something so foreign to our intuition that we do not yet have language for it. Something that does not vibrate, because vibration itself is a property that emerges only at higher levels. Something more abstract than substance, more fundamental than field, more silent than the foam. We are about to take that step. We are about to leave behind the comfort of fields and ripples and enter the territory of pure speculation, the place where current physics gives way to the wildest and most beautiful proposals that human minds have ever conceived. Strings, loops, the Planck scale, the edge of measurable reality. Keep breathing slowly. The descent continues. There is a place where physics stops being a description and starts being a prayer. We have arrived at that place. We have walked through the comfortable image of solid matter, through the empty cathedrals of the atom, through the strange refusal of quarks to stand alone, through the vast catalogue of the Standard Model, through the dissolution of the particle into the field, and the field into the humming foam of the quantum vacuum. We have descended further than most people are ever invited to descend. And now we stand at the edge of what physics can currently describe at all. What lies below this edge is not yet science in the ordinary sense. It is something stranger. It is the place where the most brilliant theoretical minds of the past half-century have proposed answers that nobody has yet been able to confirm, where the mathematics becomes so beautiful and so demanding that experimental verification may be permanently out of reach, where the questions themselves begin to shimmer with a quality that feels almost theological. We are about to walk into the territory of theories that cannot yet be tested. Hold them lightly. They may be true. They may be wrong. They are the boldest guesses our species has yet made about the deepest layer of reality. Let us begin with strings. In the late 1960s, around the same time that quarks were being confirmed inside the proton at Stanford, a young Italian physicist named Gabriele Veneziano was studying a particular mathematical pattern that kept appearing in particle collisions. He stumbled, almost by accident, on an equation that described the pattern with strange elegance. He published the equation. He did not yet know what it meant. Other physicists looked at the equation and slowly, gradually, began to realize that it described something extraordinary. The equation worked if you imagined that the particles involved were not points at all. The equation worked if you imagined that they were tiny one-dimensional filaments, strings. This was the seed. Over the next several decades, the idea grew into one of the most ambitious theoretical frameworks in the entire history of science. String theory. The picture is this. At the deepest level of reality, beneath the fields, beneath the foam, beneath every other description we have so far constructed, there are no point particles, and there are no vibrating ripples in fields. There are only strings, tiny filaments of pure energy, far smaller than anything we could ever directly observe. Each one, a one-dimensional line that exists in space and vibrates with a specific pattern. The string can vibrate in many different ways. It can hum at a low frequency or a high one. It can twist and oscillate in complex multidimensional shapes. And here is the heart of the idea. Each different vibration pattern of the string corresponds to a different kind of particle. A string vibrating one way appears to us as an electron. A string vibrating a different way appears to us as a photon. A string vibrating yet another way appears as a quark, or a gluon, or a Higgs boson, or any of the other inhabitants of the Standard Model. The strings themselves are all identical. There is only one kind of fundamental thing. What varies is the song that the thing is singing. The universe, in this picture, is a symphony. The particles are not objects. They are not even ripples. They are notes. Different harmonics of a single underlying instrument, played simultaneously across all of space, weaving together into the rich and complex score that we experience as reality. The chair beneath you is a chord. Your hand is a chord. The light reaching your eyes is a chord. All of it, every solid and every shadow, is the music of strings vibrating in patterns whose total composition is the universe itself. I want you to feel how beautiful this idea is before we complicate it. The strangest thing about string theory is not what it claims. The strangest thing about string theory is how naturally it removes a problem that physicists have struggled with for a century. The mathematics of point particles, when combined with the mathematics of gravity, produces infinities. Equations break, predictions become nonsense. But if the particles are not points, if they are extended one-dimensional strings, the infinities disappear. The equations behave. Gravity, which fits into nothing else, fits naturally into a theory of strings. For this reason alone, many theoretical physicists have spent their entire lives pursuing the idea. But string theory comes with a price, a strange and beautiful price. In order for the mathematics of string theory to work, in order for the equations to remain consistent, the strings cannot live in 3 spatial dimensions. They need more. Different versions of the theory require different total numbers of dimensions, but most of them require 9 or 10 spatial dimensions, plus the dimension of time, 6 or 7 more spatial directions than we are aware of in everyday life. Where are these dimensions? Why have we never noticed them? The proposed answer is that they are curled up, folded so tightly, on a scale so unimaginably small, that we move through them constantly without ever realizing we are doing so. Imagine a long, thin garden hose stretched across a field. From far away, the hose appears to be a one-dimensional line. You could only move along it, but if you walked up close, you would see that the hose has a second dimension. You could walk around its circumference as well as along its length. At a distance, the second dimension was invisible. Up close, it was always there. String theory proposes that the universe is like this. The 3 large dimensions of space that we know about are simply the longest directions of the hose. The other dimensions are wrapped up so tightly, at scales so close to the Planck scale itself, that we never notice them. They are not somewhere else. They are right here, right inside the space where you are sitting, curled up in directions so small that no instrument we have ever built could possibly detect them. Hold that image gently. Even now, in the room you are in, even within the space between the cells of your body, there may be additional dimensions wrapped into shapes too small to perceive. Reality may have more directions than you have ever imagined, hiding in plain sight, woven into every cubic millimeter of existence. Now, I have to be honest with you, because honesty is part of what makes this descent meaningful. String theory, for all its mathematical beauty, has never been experimentally confirmed. Not once. After 50 years of work by some of the most brilliant minds on Earth, we have no direct evidence that strings exist. The energies required to probe the scale at which strings would become visible are so enormous that no collider we could ever build on this planet, perhaps no collider that could ever be built in any solar system, would be powerful enough to see them. String theory predicts a universe far richer than the one we can currently measure, but it remains, for now, a hypothesis. A magnificent, mathematically deep, intellectually persuasive hypothesis, but still a hypothesis. This is why some physicists have turned to a different idea, a different vision of the bottom. It is called loop quantum gravity. If string theory says that the smallest things are tiny vibrating filaments living inside a smooth space with extra dimensions, loop quantum gravity says something more radical. It says that space itself is not smooth. Space itself is not continuous. Space, at the deepest level, is woven from discrete loops, like a fabric made of unimaginably tiny rings. Each one a fundamental unit of geometry, from which all the larger distances we measure are built. Picture a piece of cloth. From a distance, it looks like a smooth, continuous surface. You could imagine drawing a line on it and moving your finger along the line in any direction. But if you bring your face close to the cloth, you see that it is not continuous at all. It is woven. It is made of individual threads, crossing and looping together, leaving small, definite spaces between them. The smoothness of the cloth at large scales is an illusion produced by the tiny scale of the weaving. Loop quantum gravity proposes that space behaves the same way. At the scales we are familiar with, even at the scales of atoms and protons, space appears smooth and continuous. You can imagine moving any distance you like, even very small distances, in any direction you like. But at the deepest level, this smoothness is an illusion. Space is woven. Space is made of loops. There is a smallest possible area. There is a smallest possible volume. The geometry of reality, at the bottom, is not continuous, but quantized. Distance comes in indivisible chunks. The fabric of the universe has a weave. In this picture, reality is pixelated. Just as a digital image, when magnified far enough, reveals itself to be a grid of small square pixels. The universe, when probed deeply enough, would reveal itself to be a grid of small geometric chunks. There would be no meaningful distance smaller than the chunk. There would be no meaningful volume smaller than the smallest cell of the weave. The smooth continuum of space that we take for granted in everyday life would dissolve into a network of discrete relationships, a graph of fundamental connections, a structure that is finite in its fineness, even though it appears to us as infinite in its smoothness. So we have two competing visions of the bottom. In one, the smallest things are vibrating strings living inside a smooth space with hidden curled dimensions. In the other, space itself is made of discrete loops, and the smoothness of geometry is an emergent property of an underlying weave. Both are mathematically rich. Both are philosophically beautiful. Both are, as of right now, unverified. What unites them is something they cannot avoid. Both theories, along with every other serious attempt to describe the deepest level of reality, agree that there is a smallest meaningful unit of length, a scale below which the familiar concepts of distance and time and cause and effect break down, a floor, or at least the appearance of a floor, beneath which the physics we know stops making sense. This scale has a name. It is called the Planck length. The Planck length is a number derived from three of the most fundamental constants in all of physics: the speed of light, the constant that limits how fast anything in the universe can travel, the gravitational constant, which determines how strongly mass attracts mass, and Planck's constant, which sets the scale of quantum effects. When you combine these three constants in a particular mathematical way, you get a length, a specific physical distance, derived from the deepest known laws of nature, that appears to mark the boundary of meaningful measurement. The value of the Planck length is approximately 10 to the negative 35th of a meter. Let me try to give you that number in a way you can feel. Imagine you take a single atom. An atom is already so small that it cannot be seen by any optical microscope. Trillions of atoms fit into the period at the end of a sentence. Now imagine you take that atom and you expand it. You grow it. You inflate it until it becomes the size of the entire observable universe. The whole atom, blown up to encompass every galaxy and every cluster of galaxies in the cosmos, a region 93 billion light-years across. That is the new size of your single atom. Inside that universe-sized atom, the Planck length would still be smaller than a grain of sand. Let the vertigo of that comparison settle. We are not speaking about something small. We are speaking about something that lies as far below the scale of an atom as a grain of sand lies below the scale of the observable universe. The Planck length is so unimaginably tiny that the word small ceases to mean what it usually means. The Planck length is the size at which our intuitions about size give up. And here is what physicists believe happens at this scale. The familiar laws of physics break down. The smooth equations of general relativity, which beautifully describe the behavior of space and time at the scale of stars and galaxies, become unreliable at the Planck scale. The smooth predictions of quantum field theory, which beautifully describe the behavior of particles at the scale of atoms, also become unreliable at the Planck scale. The two theories that have served us so well in their separate domains begin to disagree with each other violently when applied to the same incredibly small region of space. At the Planck scale, gravity becomes comparable in strength to the other fundamental forces. The fabric of space-time, which appears smooth and stable at every scale above this one, may itself begin to fluctuate. Some physicists describe the Planck scale as the place where space-time becomes a foam, frothing and trembling with quantum uncertainty, where the very notions of distance and direction lose their precision. Cause and effect, the orderly relationship of one moment leading to the next, may become tangled at this scale. The before and after of events may blur. The geometry of reality may stop behaving like geometry. And the most haunting possibility of all, The Planck length may not be merely a scale at which our current theories break down. The Planck length may be the bottom. There may be no meaningful smaller. There may be no measurable distance below it. The very concept of subdividing space further than this may be physically meaningless, not because we lack the tools to measure it, but because there is genuinely nothing there to be measured. The universe, at this scale, may simply stop being divisible. If that is true, then we have found something extraordinary. We have found a possible answer to the question we have been chasing through this entire descent. The smallest possible unit of reality may not be a particle, or a field, or a string. The smallest possible unit of reality may be the Planck scale itself, the discrete pixel of space-time, the irreducible cell of the cosmic weave. Below this scale, the question of size becomes a question without an answer, because the very property of having a size requires geometry, and geometry below the Planck scale may not exist at all. Or it may not be true. The Planck scale may simply be a horizon beyond which our current theories cannot see, but beneath which something deeper continues to unfold. Just as the proton once seemed fundamental and was later revealed to contain quarks, just as the quark once seemed point-like and may yet reveal further structure, the Planck scale may turn out to be another false floor, another door we have not yet learned how to open. We do not know. Nobody knows. The honest answer at this depth of the descent is that we have arrived at the edge of human knowledge, and the territory beyond it has not yet been mapped. This is what it means to stand at a frontier. This is what it feels like to look outward from the edge of what your species has so far understood, knowing that the questions ahead of you may not be answerable by any technology you will ever build, may not be answerable in your lifetime, may not be answerable in any lifetime. The deepest layer of reality may be permanently veiled from us, or it may be revealed tomorrow by an insight from someone now studying in some quiet university library. The not knowing is not failure. The not knowing is the open door at the end of the corridor. Take a slow breath in this place. You are standing where centuries of human curiosity have brought us, and no further. You are looking at the boundary between physics and philosophy, between measurement and contemplation, between the things we can hope to one day verify and the things we may only ever be able to wonder about. And yet, even here, even at this remote and trembling edge of knowledge, there is one more idea waiting. One final proposal that does not even bother to ask what the smallest piece of matter is, because it suggests that matter itself may not be the right category at all. A proposal that asks whether the universe, at the bottom, is made of stuff in any sense, or whether it is made of something far stranger, something that has no size, something that has no substance, something that exists prior to space and time themselves. A proposal that whispers very quietly that the universe may not be made of things at all. The descent has one more layer. There is one more idea, the last one, the strangest of them all. It comes from a man named John Archibald Wheeler. If you have not heard his name, that is all right. He spent most of his life out of the public eye, teaching at Princeton, advising graduate students, working quietly on the deepest problems in physics. He was the man who coined the term black hole. He was the man who helped develop the theory of nuclear fission. He was a student of Albert Einstein and a teacher of Richard Feynman, two of the most luminous minds of the 20th century, and he sat in conversation with both of them across decades of his long life. By any measure, John Wheeler was one of the most serious and respected physicists of the modern age. And toward the end of his life, after a lifetime of work on matter and energy and the geometry of space-time, Wheeler proposed something that sounded almost like mysticism, but that he insisted was a literal scientific hypothesis. He suggested that the deepest layer of reality might not be made of matter at all, not particles, not fields, not strings, not loops. Something even more fundamental, something that has no size, no shape, no substance. He suggested that the deepest layer of reality might be made of information. He gave the idea a name. He called it from bit. It meaning every physical thing in the universe, every atom, every star, every galaxy, every person. Bit meaning a single unit of information, a yes or a no, a 1 or a 0, the smallest possible answer to the smallest possible question. Wheeler proposed that every physical it in the universe ultimately derives its existence from a vast and unfathomable network of bits, of fundamental yes or no distinctions, woven together in patterns so intricate that they appear to us as matter and energy and space and time. You have to sit with this slowly, because it is genuinely strange, and it deserves to be taken seriously rather than dismissed. The idea is not that the universe is a computer. The idea is not that we are living in a simulation. The idea is something deeper and more difficult. The idea is that at the bottom of reality, there is no substance. There is only distinction. The universe does not consist of stuff that has properties. The universe consists of a vast unfolding pattern of differences. This is here, that is not here. This is one way, that is the other way. The yes and the no, repeated in every possible configuration, across every possible scale, generating the appearance of matter and motion as a kind of emergent surface effect on something more fundamental. Wheeler did not arrive at this idea casually. He arrived at it through decades of struggling with the deep problems of quantum mechanics, where the act of measurement seems to play a strange and irreducible role in determining what reality actually is. In quantum experiments, particles do not have definite properties until they are observed. Their existence, in some real sense, requires an act of asking. A question must be posed before an answer can crystallize, and Wheeler began to suspect that this was not a quirk of small things, but a clue about the nature of reality itself. Reality is not a collection of objects waiting to be measured. Reality is the ongoing process of measurement. The universe is not a noun. The universe is a verb, an asking, a continuous unfolding of questions and answers, distinctions and choices, in which every physical thing is the trace of a yes or a no posed at some level deeper than physics can currently reach. If this idea sounds difficult to hold, that is because it is. It dissolves the comfortable picture of reality as a place full of things into something far stranger, a place that is not made of things at all, a place that is made of asking. And Wheeler is not alone. In recent decades, his idea has been taken up by other physicists working on a closely related proposal called the holographic principle. The holographic principle emerged from the study of black holes, where physicists realized something completely unexpected. The amount of information that can be stored inside a black hole does not depend on its volume. It depends on the surface area of its event horizon. The two-dimensional boundary of the black hole, the surface beyond which nothing can escape, contains all the information about everything inside the three-dimensional interior. The interior is, in a sense, encoded on the boundary. This was strange enough as a fact about black holes. But theoretical physicists soon began to suspect that the principle might apply more generally, that it might apply to the entire universe, that the three-dimensional reality we move through every day might be a kind of projection, an emergent property of information encoded on a vast two-dimensional surface at the edge of the cosmos. The universe, in this picture, would be a hologram. The depth and richness and dimensionality we experience would be a sophisticated illusion generated by a flatter, more fundamental structure of information at the boundary of everything. Take a moment with that. Allow it to feel almost too much. The chair beneath you, the breath in your chest, the depth of the room you are sitting in. All of it, possibly. The projected appearance of a pattern of information encoded somewhere else. Not stuff, not particles, not fields, distinctions. Yes and no, repeated in ways more complex than any human mind has ever fully imagined. Whether the holographic principle is literally true, or whether it is only a deep mathematical curiosity that points towards something we have not yet fully understood, no physicist alive can tell you with certainty. But the principle has survived decades of mathematical scrutiny. It fits with several of our deepest theories. It is taken seriously by some of the most careful thinkers in modern physics, and it pushes us toward a conclusion that the entire descent of this script has been preparing you for. Reality may not be made of matter at all. Reality may be made of relationships, of distinctions, of the act of distinguishing one thing from another, repeated in patterns whose total composition is the universe itself. The universe may be less like a machine and more like a question, an ongoing question, a question that is in some sense asking itself, generating the answer that we call existence, as the act of asking continues. There may be no bottom, there may only be the asking. Let this sit. Let it be uncomfortable. Let it be beautiful. Let it be whatever your mind needs it to be in this slow hour. Now I have to be honest with you about something important, and I want to say it gently, because the honesty matters. Physicists do not know which of these pictures is correct. Not one of them is confirmed. String theory, loop quantum gravity, the holographic principle, the it from bit proposal, none of them has been experimentally verified. Each of them is a beautiful guess, drawn from the convergence of mathematics and intuition, offered as a possible answer to a question whose true answer may still be far beyond us. The deepest layer of reality, as of this moment in human history, remains unknown. The smallest possible unit of reality is a question we are not yet equipped to answer. I want you to hear that not as a disappointment but as an invitation. Because every generation of humans, going back to Democritus in his coastal Greek air, has believed it stood at the final layer. Democritus believed in the indivisible atom. Dalton believed in the chemical atom. Rutherford believed in the nucleus. The mid-century physicists believed in the proton, then in the quark, then in the field. Now we believe, with appropriate humility, that perhaps we are beginning to glimpse something below the field, a weave, a symphony, a pattern of information, maybe, maybe not. And our great-grandchildren, if we are fortunate enough to leave them a world in which curiosity is still cherished, may look back on our current theories, the way we now look back on the picture of the atom as a tiny solar system, a useful step, a productive error, a picture that pointed in the right direction without arriving. You are part of that lineage. You are part of a long chain of beautiful, fertile, productive wrongness. Every human who has ever asked what the world is made of has been wrong in some way. Every human who has ever asked the question has also been a little less wrong than the human who came before. The descent through atoms and quarks and fields and strings and loops and information is not a story of failure. It is a story of patience, a story of generations of minds, none of them complete in themselves, each of them passing a slightly better question to the next. And the question may never fully resolve. That too is all right, because perhaps the smallest possible unit of reality is not a thing to be found. Perhaps the smallest possible unit of reality is the act of looking, the asking, the wondering, the slow human work of refining our questions until the universe answers a little more clearly. Perhaps the bottom of reality, if there is one, is not a particle or a field or a bit. Perhaps the bottom is the meeting place where consciousness encounters the cosmos and asks, again, in the way our species has asked for thousands of years, what is this? What am I? What is everything made of? Now, I want you to come back, gently, slowly. Come back to the room you are in. Come back to the air moving softly in and out of your chest. Feel the weight of the blanket if there is one. Feel the surface beneath you, the bed or the couch or the chair. Feel the small temperature of your skin, the soft sound of your own breath, the quiet presence of your body returning to your awareness after this long journey through scales that no body could ever directly travel. You are here. You are still here. The descent did not take you anywhere. You never left this room, and yet everything has changed. Because every cell in your body is a cathedral of empty space. The thing that holds you to this bed, the thing that gives you the comforting solidity of your own weight, is the energy of invisible bonds, vibrating in the heart of every proton, in every atom, of every molecule, in every cell. Your body is mostly absence, held together by ceaseless work. Your body is mostly silence, interrupted by the constant low music of fields that fill the entire universe. The same electron field that hums in your fingertip, hums in every star you have ever seen. The same Higgs field that gives mass to your bones, gives mass to galaxies you will never visit. You are part of the music. You have always been part of the music. And every atom inside you, every smallest unit of the supposed solidity of your form, may itself be only a vibration, a note in a song, a localized excitation of something deeper, a standing wave in a sea whose bottom we have not yet found. And if Wheeler was right, even that wave may itself be made of something stranger still, a single bit, a yes, a no. A small distinction in an immense unfolding pattern that has been asking itself into being since long before there were stars. You are made of patterns older than time. You are made of distinctions that may extend through dimensions you cannot see. You are made of vibrations in fields that stretch to the edge of the cosmos. You are made of relationships that have no center and no edge. And tonight, in this small dark room, in this small, soft moment, all of those vast and ancient processes are gathered together briefly into the shape of you, breathing, resting, listening, becoming sleepy. This is what you are, not a body of solid stuff, not a thing among other things, a song the universe is singing to itself in the quiet hours, using your bones and your breath and your slowly closing eyes as the instrument. The night is gathering around you now. The sounds of your home are softer. The light in the room is dimmer. The thoughts in your mind are loosening, drifting, slipping into the long, slow current that will carry you towards sleep. And as you drift, I want you to remember, very gently, that the particles that make up your dreaming mind are not particles at all. They are ripples in a sea that has no shore. They are notes in a music that has no final chord. They are questions still being asked by a universe that is still, in this very moment, making itself. Rest now. Let the descent close. Let the questions remain. You are made of the same patient mystery that has been unfolding since the beginning. You always have been. Sleep softly inside it. Stay with me for a little longer. The descent is finished, but we are not quite done. Notice that you are still here, still breathing, still wrapped in the same body that began this journey, in the same room, on the same bed, beneath the same gentle weight of the same blanket. Nothing visible about your life has changed. The clock has moved a little, the night has deepened a little, but the surface of your existence is exactly as it was when we began. And that is the strangest thing of all. Because everything we have explored tonight, the cathedrals of empty space inside every atom, the boiling storm of quarks and gluons inside every proton, the vast humming fields that fill all of existence, the possible vibrations of strings in folded dimensions, the possible threads of information weaving the deepest layer of reality, all of it has been happening inside you the entire time, while you sat and listened, while your mind followed the descent, while you breathed slowly in this quiet room. The mystery never paused. The mystery was never elsewhere. The mystery was always right here, inside the cells of your hand, inside the slow rise and fall of your chest, inside every atom of every part of you. And it will continue. Tomorrow morning, when you wake, you will reach for something. A cup, a glass of water, the edge of the blanket as you push it aside. And in the moment your fingers close around that object, every layer we have explored tonight will be present in the contact. The atoms in your fingertips will be cathedrals of empty space, brushing against other cathedrals of empty space. The protons inside those atoms will be roaring with the internal storm of quarks and gluons, holding themselves together by ceaseless invisible work. The electrons will be smears of probability rather than little balls. The fields will be humming. The vacuum between the atoms will be foaming with virtual particles that flicker in and out of existence faster than any clock could measure. And somewhere beneath all of that, if the deepest proposals are correct, the threads of information or the strings of vibration or the loops of woven space will be doing whatever they do in patterns we have not yet learned how to see. All of this will be happening in the simple act of lifting a cup. Every doorway you pass through tomorrow will be a passage through a region of space saturated with overlapping fields. Every face you look at will be a configuration of standing waves whose composition is older than the planet. Every word you speak will be a small disturbance of air molecules whose existence depends on the same forces that have shaped the cores of stars. The universe will not be hiding tonight, and the universe will not be hiding tomorrow. The universe is not somewhere far away. The universe is your morning, your kitchen, your breath, your skin, your slow, ordinary day. It has always been so. You have simply learned in this small, dark hour to recognize it. Take a moment to feel where you stand in the long lineage of asking. 2,400 years ago, a man named Democritus stood on a Greek shore and wondered what the world was made of. He could not test his idea. He could not measure anything smaller than what his eyes could see. He simply thought and reasoned and offered a guess. 200 years ago, John Dalton sat with his careful records of chemical reactions and refined the guess into something closer to truth. A little over a century ago, Ernest Rutherford fired tiny bullets at gold foil and discovered that the supposed solid atom was mostly empty. In our own time, thousands of physicists work patiently around a 17-mile ring of magnets beneath the border of France and Switzerland, asking the same question with instruments that Democritus could not have imagined. John Wheeler sat in a study at Princeton and wondered whether the answer might be made of pure information. You are part of this chain. Tonight, in this quiet room, in this slow hour, you have joined a lineage of human beings that stretches back across millennia, all of them looking at the world and asking the same simple question. What is this made of? What am I made of? What is everything made of? None of them found a final answer. All of them passed a slightly better question to the next. And here you are, the most recent link in that unbroken chain, lying still in the dark, the asking continuing through you as it has continued through everyone who came before. The chain will not stop with you. Someone, somewhere, perhaps not yet born, will refine the question further. Will find a way to test what cannot yet be tested. Will see something we cannot yet see. The descent will go on. And whether or not the bottom is ever reached, the asking itself is the most beautiful thing our species has ever done. Now let yourself rest. The work of this hour is finished. The thoughts are loosening. The night has gathered around you completely. The sounds of your home are soft, almost gone, and the breath in your chest has slowed to the long, quiet rhythm that comes just before sleep. Feel the universe inside you, not somewhere else, not somewhere far. Right here, In the small, warm space of your body, every layer of reality is humming at once. The fields, the foam, the strings, if they are there. The bits, if they are there. The patient mystery that has been unfolding since long before this planet existed is happening now. In you, as you. You are not separate from any of it. You are not watching it from outside. You are one of its momentary shapes, a configuration of pattern and pause, a small standing wave in an ancient sea. And as your eyes grow heavy, and the room grows softer, and the descent of sleep begins its own gentle pull on you, remember this: the universe does not need you to understand it for it to keep happening. It will continue inside every cell of your body all night long, humming, vibrating, asking, becoming. You can simply rest. You can simply let go. The mystery will be here in the morning, exactly as it was tonight, exactly as it has always been, waiting quietly inside the cup, inside the doorway, inside the first breath of the new day. Sleep now, small bright pattern in the long song of everything. The asking will continue without you, and with you, and as you.